So this talk, I don't usually do introductions to my talks very much. I usually just get on with it, but this one I feel like I ought to. This talk is his fault, it's James's fault. So James, I didn't know he was talking here tonight, but James invited me to talk at a ThoughtWorks alumni event a month or two ago. And I thought that'd be fun, and I thought what'd be a fun topic. And it was just so I did a very, very short talk. It was 15, 20 minutes or something like that on this topic. This is something that kind of spun out of, I'm working on another book at the moment. The working title is Modern Software Engineering. The idea, it's a bit philosophical. I'm not quite sure it's going to be as popular as my previous book. It's a bit esoteric, but I'm enjoying writing it, so what the hell. And I'm kind of philosophizing a bit about what software engineering is or what it ought to be. And this kind of spun out of that. I had a Twitter conversation with somebody, and at one point this person, who to my shame I can't remember who it was that said this now, so I can't attribute it appropriately, but this person that I was having the conversation with said, if we were to come up with good ideas for what software engineering really ought to be, they would be durable. They would be as true in 100 years' time as they are today, because that's what engineering is about. It's about trying to come up with ideas that are kind of, profound in meaning. And I think one of the mistakes that we've made in our profession over the years is trying to pick up more ephemeral things. So I thought it'd be fun to try and think about in those sorts of terms. So what would software development, software engineering be like in 100 years' time? What are those durable ideas? What are the kinds of things that are not just a fashion in our industry? Because there's quite a lot of fashion in our industry. There's quite a lot of those ideas that are quite less important, I think. And so that's the idea of this talk. This is the first long version of this talk. So I have no idea how long I'm going to take to do this. I've done the short version at ThoughtWorks, and that's the only version before. So you're my experimental victims, I'm afraid, to try and figure out whether I can make a talk out of this or not. So starting off, if we're trying to extrapolate forwards in terms of what software, what sorts of ideas are durable over long periods of time, one way of doing that is to think back. What were the kinds of ideas that were happening 100 years ago? What was software development like 100 years ago? And if you're anything like me, you're probably thinking something like this. It's absolutely nothing. There was no software development 100 years ago. And you're kind of correct. But one of the things that you have to remember is that people were exactly as smart as we were then, and they did some clever things too. And one of the clever things that they did in those days was that they came up with some various machines. So there was the Jacquard loom and the Hollerith machine and those sorts of things. This is a Hollerith machine. This is the thing that did the census at the turn of the 20th century in the States. So this is a tabulating machine, and this is a computer. This person here is a computer who is programming the machine, and this is what she's producing. She's producing, and mostly they were women that did this kind of job for a long time, from the early days on into the kind of 60s. There was often late 50s and 60s. It was often mostly women that did this kind of stuff. And this is what she was producing. She's producing a program on a card that would drive this machine. And I thought it'd be interesting to think about what was the algorithm that they were using. And this is roughly the algorithm that they were creating for this tabulating machine. This is written in SQL, or an approximation thereof. And the thing that I think is kind of intriguing here is that this is recognizable to us. This is the sort of thing, we could imagine writing a system and having to write some SQL statements like this to solve this problem. There's something about the granularity of ideas that seems durable, that seems persistent. We've tried really, really hard to try and raise the level of abstraction as we've gone through evolving our tools and our techniques, with relatively limited success. There are a few points where we've managed to achieve that. The step from machine language to higher level languages perhaps, but few real big leaps in progress. So there's something there that's kind of interesting in terms of that. For the rest of this talk, I'm making kind of a big assumption, and the big assumption is that they're not doing all of the programming. that we are still involved. We haven't delegated this to somebody else. So let's assume, for the sake of the next 45 minutes or so, that part of the problem is that we've got to fit stuff inside our heads. Software still needs to fit inside a head. So what sorts of ideas are durable? Well, given the constraint of needing to solve complicated, increasingly complicated problems, fit them inside of our head, what sort of problems what sort of techniques could we use to scale up to really get big improvements in productivity, quality, and so on? Is it about language design? I think no. I think language design is not, as I said, I think there have probably been two, arguably three kind of significant, moderately significant steps in terms of performance and efficiency and quality over time through language, but I don't think we've made big leaps. I don't think there are many more big leaps to be had. So I don't think it's language. So why not? Part of the why do we focus so heavily on language? Part of the reason is because we like writing languages. If you're a techie nerd, like I assume most of us in this room are, it's a lot of fun writing a language. I don't know if you've tried, but I've had a couple of goes in the past, and it's a lot of fun. It's exciting stuff to do, and we come up with lots and lots of these languages. But if I'm honest, I don't think that they really, most of them don't really move the dial. You don't get pointer bugs if you make the shift from C++ to Java, but it's not a massive difference in terms of the granularity or the abstraction or the tools of modularity between the two. You could argue that functional programming languages give you a step forward, and I think that there are some advantages there, but I don't think they are a silver bullet either. And so I don't think language is the silver bullet. I don't think that's the thing that's going to give us a significant improvement in terms of the way in which we can approach things. I think mostly language design is about fashion. And I think we concentrate on the wrong things a little bit in terms of trying to do that. We're trying to optimize to minimize typing. And I don't think minimizing typing is really where it's at. So, my prediction, there will be no great leaps in productivity because of programming language. I think it's unlikely that that programming languages are going to give us a significant step forward in our capability and our ability to do things with greater quality. I think that there's a slight caveat here, which is I think that there will be some room, that there's always room for kind of focused, domain-specific languages where you target a specific problem or sphere with a domain-specific language. And I think there's some utility there, there's some usefulness there in that kind of thinking. But general-purpose programming languages, I'm not sure that I believe that there's going to be a big leap in terms of what we're able to achieve or what we're able to do. And I don't think we've seen one for a long time. I think we fool ourselves sometimes because of the fashion aspects of our industry that we're making progress, and sometimes the tools are not. I'm trying at the moment to get the enthusiasm to write a sample website in a 1990s set of tech and a 2019 set of tech, and I'm fairly sure that the amount of code that I write will be fairly similar. I'm not sure there are big leaps in writing a web page in those different techs. So next prediction. There won't be a huge change in the level of abstraction. That thing, when we were looking at the Hollerith machine, that kind of granularity of a problem, there's something inherent there. There have been lots of attempts to raise that level of abstraction, because in the early days that was the thing that gave us a big step forward. By making the jump from assembler to a high-level language, that was a big step forward in productivity. And we've been looking for that. So the classic one that I've seen in my career, kind of reinvented kind of 5 or 6 times probably, is sort of visual programming. So wouldn't it be wonderful if you could just draw a picture of the system and that would be it, that would be a program. Except it doesn't really work, because either the picture is too general case and too abstract and not detailed enough to solve real world problems. They demo beautifully, those sorts of systems, but they don't really solve real problems on the whole. You've got to get down to the nitty-gritty detail. You've got to start worrying about variables and scope and loops and all of that kind of Turing machine kind of gubbins at some level. So I don't think we're going to see a big change in the level of abstraction. There's a caveat. I remember what I said before, this is about fitting stuff into human heads. Part of this, we might expand the capacity of our heads. I think that's a likely outcome that we're going to see. We're going to be augmenting ourselves. We're already starting down that road to some degree. There's probably some stuff that's going to amplify some things, and that might change a little bit in terms of the way in which we think about ideas and concepts and stuff like that, because we'll be able to cope with bigger ideas perhaps. But short of that, I'm not so sure. The next thing to consider, I think, that are very, very fashionable, very common to think about in terms of the tools of our trade are frameworks. Frameworks that allow us to kind of compute things more easily or organise ourselves more easily. And again, I'm not quite sure that I see significant step forwards in terms of frameworks. I think there's some more caveats here in terms of, rather than languages, I think there are some more options. There's some missing stuff, particularly in the sphere of continuous delivery. I think the tools are quite significantly immature at the stage in the continuous delivery space, and there's room for improvement there. I could imagine systems that were much more integrated, it's much more built into the development process that would make things. And you could kind of think of those in terms of frameworks. But on the whole, I don't think that frameworks are going to solve the problem. Again, part of the reason is because everybody's got their favourite framework. There's this kind of fragmentation of effort and ideas and techniques, and there's always a new one coming along. How many frameworks have you got in your kit bag? How many times have you kind of, Angular programmers, anybody, Node.js programmers, all of these things, they come along and they go and they move on, and there's the next fashionable thing coming along next. So we've got all of these frameworks, that kind of add, and partly the difficulty with these things is that really what the focus is they're focusing on the wrong things again, to my mind. I think that what people tend to be focusing on when they're trying to write these frameworks is not the stuff that really matters. What people are mostly trying to do in these circumstances is they're trying to optimize to reduce typing. And typing isn't the problem. You can learn to type faster. My limit on writing software isn't the speed with which I type. I don't really mind if I've got to type some more characters, but my code is easier to read and is more expressive. That's okay with me. But thinking, I want to optimize for that. I want to be able to try and be able to hold more complex, more involved ideas and deal with things at a different level. That's where the real optimization comes from, I think. So thinking in terms of these sort of really durable stuff, I think that we're thinking, the model of the way in which we think about and undertake and philosophize about software development, I think is really, really important. I haven't quite got the click-through right on this. So my prediction, there may be some big steps facilitated by frameworks. Particularly, I think there's something interesting in terms of the move to cloud-based systems, serverless systems. One of my particular favourite architectural patterns, asynchronous event-based microservices style architectures. And I can imagine significantly more sophisticated tooling for build and test and evaluation of those systems integrated into the deployment and the configuration management. I can imagine that kind of stuff. So I can imagine some steps in terms of frameworks that would give us a step forward in that sense. But I think only as part of this bigger rethink in terms of architectural things. I don't think there's going to be a magic bullet that allows you to write, an NT, a relational database-backed service better than the frameworks. I'm not quite sure that Ruby on Rails is a significant step forward beyond Visual Basic, to be honest, in terms of the levels of abstraction and the kinds of systems that you could write. So, frameworks alone are not enough, except in a broader context, to my mind. I do apologise if I trample on any of your sacred cows during this talk. It's that kind of talk. The next one is programming paradigm. There's a lot of stuff these days at the moment. The functional programming paradigm is kind of, leading a lot of stuff, and there's a little bit of religious wars going on, I think, between some of the different schools of programming in this space. Programming paradigm, this too, I'm not quite sure that there are going to be any major steps forward in terms of programming paradigm. This may be surprising because then that's something that we're kind of looking for. But again, this gets back to that problem that I pointed out at the beginning, which is the idea that there's something fundamental about the granularity at which we need to solve problems that execute on computers. So that's, the programming paradigm, there are limits to how far we can go. There are parts of that problem that programming paradigm helps us address, but I think we've solved most of those parts. And so I'm not quite sure that that's going to move us forward very much either. So this is an extremely risky prediction. I recognise this, it's just personal viewpoints. Programming will still be procedural, object-oriented and functional in parts in 100 years' time. I think each of those different bits of programming, each of those different kind of paradigms brings something different to the party. I don't think that functional programming is enough on its own. I think that functional programming adds something to object-oriented programming in the way that object-oriented programming added something to procedural programming, but each of those things adds value and solves a different part of the problem. And I'm not quite sure, it's obvious to me where there are gaps. I confess I am an old school OO programmer, so I'm probably the wrong person to talk about functional programming, but it's my impression in the industry as a whole, it's currently fairly fashionable to beat up on OO programming and to disdain it, and I think that's a mistake. So I've heard people say OO failed, and all I can do is kind of laugh in their face, because OO allowed us to build systems on the scale that we have computer systems now. Without object orientation, we wouldn't have the operating systems that we have now. We wouldn't have the cloud. All of those things came from that sort of thinking and those sorts of technologies. And so it gives us something. It gives something important. It's an enabling step to creating and managing and living with and understanding bigger, complex systems. And it gives us an organisational approach. So I'm a little bit sad when people disdain object-oriented programming. Mostly when I dig into people talking about that kind of stuff, it's for what I would think of as fairly naive thinking about object-oriented design. Mostly what they don't like is inheritance. Me too. I'm not a huge fan of inheritance, but that's kind of that's an argument that we had in the 80s and, and kind of got sidelined in the 80s. Object-oriented programming is more about composition than it's about inheritance. So I think OO will still be there, alongside functional programming, because that does bring something additional to the party. The other thing that I think that there is a gap, and I think that the gap is here, is that we're missing programming paradigms that deal with things at the service level. And we don't have that in any of our languages or any of our frameworks. And there are frameworks that kind of add some of that stuff, but I think more ingrained, more obvious kind of ways of defining the boundaries of a service and so on. I think there's some work to be done there, and I think I expect to see things continue to move over the next few decades in that direction. Some ideas are more durable than others, and one of the ideas, so I mentioned this book that I'm writing, and I'm trying to find these durable ideas, and I'm on the fence about whether to include test-driven development or not. Because test-driven development is a practice that is very, very, very close to my heart. Test-driven development, I think, is one of the deepest, most profound engineering practices that we have discovered for software development, and it is not widely enough practiced, in my opinion. I think in part, so I would colour this kind of orange rather than red. I think that test-driven development will be part of the future. I think it must be, because you need some mechanism to validate that the work that you're doing is what you think it is. And test-driven development gives you that. The problem with test-driven development is we got the words wrong. It's not about testing. And I know that's an old saw. For this crowd, I assume that you're all on board with understanding that it's not about testing, it's about design. But it's really important, the impact that it has on design. Test-driven development is what drives some of the better behaviours and allows us to design higher quality software with more confidence and to move more quickly. So I think test-driven development in some form will have an impact. You have to have that feedback. You have to have a mechanism, an approach that allows you to understand what it is that you've done and what the implications of changes to that stuff are. So I think that test-driven development will be a cornerstone of software engineering, but it won't be called test-driven development. We'll think of another name. We tried that. Some of the thought workers back in the early 2000s by coming up with behaviour-driven development. We tried to change, we tried to move the dial with some limited success, but we didn't quite move it far enough. But I still think it's important. This is another very, very risky prediction because test-driven development hasn't really captured, the minds of most software developers, which I think is sad. But my hope, really more than anything, is that when a kindergarten child learns to write her first line of code, she does it in the context of test-driven development, or whatever we call it then, in 100 years' time. That's what I hope, because that's the way that we should write code. Rather like learning accountancy, you do double entry bookkeeping from day one when you're learning accountancy. It's the same kind of thing. But then I've kind of talked about stuff that doesn't count so far. But what are those really durable ideas? And the first one is iteration. Iteration is fundamentally important. I can't imagine any approach to software development that we could consider talking about in the context of being an engineering discipline that wasn't iterative. I read one of those mind-expanding books last year. It kind of completely blew my mind, and I recommend it to you if you're at all interested in science. It's called The Beginnings of Infinity, or The Beginning of Infinity by David Deutsch, who's a theoretical physicist and a bit of a philosopher on the subject of science. And what Deutsch talks about is he talks about a whole bunch of stuff. It's a really deep philosophical work on how science works. But one of the things that Deutsch talks about is he talks about these ideas, these infinite ideas, the scalable ideas. The best example I can give you is the difference between writing systems. The early writing systems were pictographic. You just draw a picture of the thing that you were representing. If you're counting goats, you draw a goat or something like that. And that's great. That's a huge step forward to be able to record things in a written form, but it's limited. It's finite, because if you see a word, if you hear a word that you've never seen before, you can't write it down because you don't know what the picture is, and nobody else is going to understand. If you make up the picture, nobody else is going to understand it. If you see a new word in picture form, you don't know what it is. An alphabet is completely different. An alphabet is infinite in its scope. Any word that you can hear, you can write down phonetically using an alphabet. Any time when you hear a word for the first time, you can write it down. When you read a word for the first time, you can sound it out. You know what kind of sound it makes. You might slightly mispronounce it, but you're going to be able to say the word. That's a big, big difference. That's the difference between a limited approach and an infinite approach. One of the things that springs to my mind when I start thinking about that is waterfall development is an inherently limited approach to software development. It puts in a definitive cap on the scope of a software project, because in waterfall development we have to understand everything about the software project at the start of the project in order to be able to come up with the plan. Therefore, it's got to fit in our heads. Iterative development allows us to decompose that into a bunch of little pieces, and each of the pieces we have to understand. We don't have to understand the whole thing. So it's an infinite approach. Iteration is deeply, deeply important, and I'm convinced that any software development worth the name will be iterative in 100 years' time. Feedback. Linked to iteration, we need to iterate and we need to get feedback, we need to get information back on the quality, the applicability, the maintainability of our work. We need to understand, we need to be able to learn what's going on. So feedback, driving our change through feedback. So one of the things, again, that Waterfall failed in is it's really, really poor at feedback. It's really a bad model for feedback, whereas an iterative, more agile approach concentrates on the feedback. Continuous delivery in particular puts feedback front and center. It's kind of focused on trying to optimize for fast, efficient, high quality feedback. And so feedback's going to be there, I think. We're going to work incrementally. We need to be able to treat, make modular systems and decompose them and put them together in different ways and work in, compartmentalize problems to be able to work this and use the tools of iteration and feedback to kind of grow these pieces independently of one another, scale out teams, all of that kind of stuff. So working incrementally too I can't imagine an engineering discipline that is not going to take advantage of that. And one that's particularly close to my heart, we're going to be experimental. The whole philosophy of engineering is that we don't know the answers before we start. Part of the power of science and engineering is that we can learn and adapt and evolve and deepen our understanding by moving through and focusing on our ability to gain new information and create new knowledge. And so being experimental is really deeply important. I was having a chat before we started about my work these days. I work as an independent consultant advising organisations about software engineering and continuous delivery and those sorts of things. And I talk a lot about the importance of being experimental in all aspects of your work. And occasionally I get fairly traditional organisations say, we can't be experimental, we can't afford to fail. And I think what that really means is that you can't afford to do anything, because unless you're going to take the risk that you might fail, you're not really going to be able to succeed either. Well, one of the things that we tend to miss about software development in general, philosophically, I think, is just how creative a discipline it is. It's an intensely creative discipline, and so we should be focusing on the creativity and the discovery and the learning that is at the roots of our discipline. And that's what our engineering approach to doing this kind of stuff should be putting front and center to my mind. The last one on my list here of these things is it needs to be empirical. This is not a theoretical thing. This is not just about kind of coming up with the perfect mathematical formula, because you can get the maths wrong. So we've also got to evaluate it in the context of real life. We've got to determine whether this is really doing what we think. And this is one of the reasons why I think test-driven development is so important, rather than the kind of mathematically provable systems. A type system in a functional language is a wonderful tool to give you feedback, but it's not enough. You can still say, my function is, increment by 1, and you add 2. You can still make a mistake. So how do you evaluate that? And that's through empirical discovery. So we need tools that allow us to do that kind of thing. I think anything that we consider to be software engineering in 100 years' time is going to include these 5 things. These seem to me the bedrock, the foundation stones of our discipline, or they ought to be. They haven't been sufficiently, but I think that they should be. Why? These are grounded in our need to learn and to deepen our understanding. Our discipline is always an act of discovery, because one of the things that we've kind of made a mistake about, the kind of $1 trillion mistake that we've made in our industry, is when we start talking about ideas like engineering and stuff like that, what's in the back of our mind is production engineering. Because if you're making physical things, producing them is a really hard part of a problem. We don't have that problem. Our problem, production for us, is clone what we've already got. It should be that simple. So our problem is about the learning and the discovery. It's the design part of the problem that is really what we're doing. Sorry, I pressed the back button while I was ranting. So software development is and always will be an exercise in learning and discovery. This will be true even if the machines are doing it instead of us. This is not about the limits of our understanding. How much you can learn and understand is about the limits of understanding, but the ability to learn and understand is really, really, at the deep roots of what it is that we do, or should be. And so we should be thinking about optimizing for that. That's what we should really be working on if we're thinking about an engineering discipline for what it is that we're doing. So even if the machines are writing the code, I think these things will be true. Even if it is them that's writing it, they will be working iteratively, they'll be employing feedback, they'll be working incrementally, they'll be carrying out experiments, and they will be working empirically, because that's the nature of the problem. That's not really about human limitations, that's just about how learning works. Whoever it is, whatever it is that's doing the learning. So, software in development in 100 years' time will be based on these ideas. These are the ones that allow us to make genuinely big steps. These are the things that I think are, why am I talking about all of this stuff to you lot? Why do you care about all of this philosophizing? Because this is the stuff that's at the heart of continuous delivery to my mind. These are the bedrocks that continuous delivery is built upon. This is why it works, to my mind. And I believe, as a result, it's a durable idea. So, in 1986, Fred Brooks, the author of The Mythical Man Month, the wonderful book about software engineering software development that was written in the 70s, wrote a paper which was entitled "There's No Silver Bullet." And what he was saying was that there are no 10 times improvements in software, in either process or technology in software development. And this kind of problem has been bemoaned in our discipline for decades. That they used to call it the software crisis in the 80s and the software gap in the 90s and all sorts of different things. But fundamentally what they're saying is that we've got acclimatized to remarkable, unbelievable Moore's law driven changes in hardware, but we don't see the same things in software. We've never seen the same things in software to the same degree. And it feels wrong. It feels like we ought to have those big wins, and they're really, really, really hard to find. And I think Fred's correct. There are no silver bullets. That's why all the stuff about languages and all that kind of stuff. But I think that there are mud bullets. I think you can get it badly, badly wrong, and I think we have. I think much of the industry of software development, certainly in terms of the way that I've perceived it through my career, has badly misunderstood what software development is. They've mistaken it for a production problem. They've tried to productionize it. They've tried to scale it up as though it's an assembly line, and that just doesn't work. That's a really, really big mistake. And so I had a client recently who hadn't been able to release any software for 5 years. They've been trying really hard. They've been, and literally 0 releases. They've done patches and stuff like that to fix bugs for particular clients and stuff, but 0 releases for 5 years. They started adopting continuous delivery. Now they did their first release into production earlier this year, and they did their second release a month later. That's a huge, huge difference. If you look at the history, you'll be probably all familiar with the HP LaserJet team story. They saw an 8-fold improvement in productivity of their development teams because they were so crap before. So you can there are definitely bad ideas. So there may be no 10x improvements if you're great, but there are 10x improvements if you're crap. That's definitely true. And one of the things that we haven't been great at in our industry is being able to rule out the bad ideas. And one of the reasons why I think that kind of engineering thinking, scientific rationalism, evidence-based decision-making, continuous improvement, all of those kinds of ideas are so fundamentally, foundationally important is because it allows us to start to eliminate the bad ideas. Why are people still trying to write software using waterfall processes? They still are. Why are they? Because it doesn't work. It's the wrong model. It doesn't fit, and it's never worked, and it's never fit. And the only way that you make waterfall work is by cheating the process. That's the only way that I've ever seen it work in my history. So, we need to be able to eliminate bad ideas as well as come up with new good ideas, and that's part of this kind of, we should be applying engineering thinking. There's a kind of another kind of supporting cast of techniques. These are more technical. These are more about the design of our software that allow us to start applying some of these ideas. These are ideas like modularity, being able to decompose systems into smaller pieces so that, again, they can fit into our heads. The work that James did and the other thought workers on kind of coming up with microservices was absolutely, about being able to do that. And this next one, separation of concerns. We don't spend enough time worrying about separation of concerns. I had a wonderful experience building an exchange with a good friend, Martin Thompson, who's widely regarded as one of the best software developers in the world. I think that's a reasonable statement. One of the things that I picked up from Martin, working alongside him for a few years, is he had an absolute laser beam focus on separation of concerns. If you're writing a piece of code and you suddenly realise it's doing two things, you pull it apart. It's always focusing on it and doing one thing. This is important. This is, again, microservices is, this is kind of that kind of thinking. It's related to that kind of thinking, but it goes deeper than that. This is the foundation of why that's important. Object orientation brought, surfaced the idea of information hiding, being able to compartmentalise and modularize our stuff. These ideas kind of reinforce one another. They're not all kind of separate. It's a bit blurry boundaries, but foundationally important. Again, we tend not to spend enough time thinking about those things. It's another one of those things that test-driven development gives us, is it gives the ability to design our software from the outside in, and so naturally it tends to lead us to better information hiding in the designs of our systems. Abstraction, capturing these ideas. I'm again, one of these on-the-fence things I'm kind of just trying to decide whether to put it in my book or not. But I think domain-driven design, using the ideas from the problem domain and that sort of thinking to create abstractions that make sense, that allow you to drive design decisions in your code, are deeply important to be able to do really good quality work. But abstraction in general is really important. That should be a tool of the trade of software developers. All of the time. How many of us think about that every day when we're writing code? Those sorts of ideas. Not enough, I think. Cohesion. I saw a great quote from Kent Beck. He said, software design is only about two things. He says you want to pull apart the things that are unrelated and you want to put together the things that are related. And that's a pretty good description. So cohesion is kind of the opposite of the separation of concerns. You want the things that are related to be close together. You want to think about those sorts of things and take those things seriously. These things are dramatically more important than how many lines of code you've got. These things are dramatically more important than what language you use. If you've got somebody that's good at these stuff, they can pick up a new language or change the language in no time. That's an easy thing. Oh, sorry, I just pressed the wrong button. Let me just skip ahead. So, why do these things matter? Because we need to decompose these ideas so that they're small enough to fit into our heads. Even if we extend our heads, that's true. We should take seriously the idea that software development is about managing complexity, and it's about learning and extending our understanding of the problem domain, our solution, the technologies that we're working with, our teammates, our capabilities as a team, all of those things. But we're learning and improving all of the time, and we take that seriously. It's all about learning. Lean practitioners talk about lean works when you focus primarily on learning and then you get great delivery as a second order effect. And software development works the same way. I spent about half an hour on the train working on the click-through of this, and it's not worked. I don't know what's going on. But anyway, prediction. Even if we mechanically extend our cognitive functions, which I think is probably likely, we're still going to need to partition problems, because however much we extend our cognitive function, it's still going to be finite. And we're still going to want to build bigger systems than we can fit in our heads. Software development is all about learning and discovery. Humanity's best approach to learning and discovery is the scientific method. Unparalleled. There is nothing that comes even remotely close. We should be learning and adapting and taking scientific methods seriously and applying it to our problem solving. That's what an engineering discipline would be. This is why iteration, feedback, incrementalism, experiments and empiricism are important. It's because it allows us to start being more scientifically rational about the way in which we undertake these. And that's what I think of as an engineering approach. Software development is also about managing complexity, trying to keep a lid on complexity and allowing ourselves to cope with that. Humanity's best approach to complexity is to compartmentalise things. The side effect, the downside of that, is that then you introduce coupling and dependencies and all that kind of stuff. We have to take those things seriously. Those are genuine first order difficult problems, but that's why they pay us lots of money, because it's a hard problem to solve. So this is why modularity, information hiding, separation of concerns, abstraction and cohesion are important. Those are the tools of the trade that allow us to put a lid on complexity. So if you don't think that I was arrogant enough to put my thing up as one of the ideas that might be true in 100 years' time, you don't know me very well. I think continuous delivery, do I think that's a durable idea? I genuinely do. I'm not actually arrogant enough to think that it might be still called continuous delivery. Don't know, don't care. It's already been called DevOps instead of continuous delivery, much to my shame. Continuous delivery is the better name, but the practice, the feedback, the evaluation, the continual small batches of work delivered frequently into the hands of users will be foundational. That will be fundamental to my mind. Why do I think that's the truth? It's because I genuinely believe that continuous delivery is based on the application of scientific style thinking to the problem of software development. Science is our species' best problem solving technique. There is no better trick to solving hard problems than science. And therefore, I think that software development will look more like continuous delivery in the future rather than less, is my belief. This is not a fad. This is not one of the fashionable things that's going to go away, to my mind. I just said that, so I'll skip. So, at its heart, continuous delivery is about iteration, feedback, incremental design, experimental and empiricism. That's kind of the meat and grist of the approach. That's really, really why it works. Everything else doesn't really matter. Whether you're using Jenkins or TeamCity or Puppet or Chef, or you're programming Ruby or Scala or what, don't care, doesn't matter. If you're doing, continuous delivery works if you're doing COBOL on a mainframe. It works if you're building embedded code in assembler. It works if you're doing SAP systems and you're configuring them. The ideas work, they're applicable. And that's because there's this deep stuff at the heart. I'll confess, when Jez and I wrote the book, this wasn't what was in our heads. But I've come to interpret this way since then. This is kind of a retrospective kind of view on what really matters here. Hopefully I've learned more in the 10 years since we wrote the book. Come on, click. So, continuous delivery through automated testing encourages the other stuff, the modularity, the information hiding, the separation of concerns, abstraction and cohesion. It amplifies our ability to do those things and use those tools to compartmentalise the problem. It allows us to build bigger, more sophisticated software as a result. It allows us to scale the teams more effectively using microservices, separation of concerns, those sorts of techniques to scale enormously if we want to. This is state of the art in terms of what's going on, and it's going to continue to be the case, to my mind. The tooling will get better. The languages might improve a little bit. But the big change is going to be the focus. It's going to be this approach on learning and design, I hope. At least it should be if we're going to achieve engineering. So a prediction. Even if the machines do write the code, they'll be adopting continuous delivery. Because it's going to be applying the scientific method. They're going to be getting feedback. They're going to be testing things. They're going to be validating things, because that's the way that you build sophisticated, complex software.